Hello, welcome to a new module on derivatives. Today we are going to review the definition of derivative and we are going to calculate some derivatives using their definition. The requirements are quite few: know what is a limit and a little basic mathematical symbology and basic operations is the only thing we need today. Let's review the definition of derivative. Recall that if f is a real function and we take a point x sub 0 belonging to the real numbers, it is said that f is derivable in that point x sub 0 if the following limit exists. The limit when h tends to 0 of f of x sub 0 plus h minus f of x sub 0 divided by h. Remember that there was another equivalent definition to this one where f of x minus f of x sub 0 divided by x minus x sub 0. But we are going to use this with h because it is a little easier. And this limit is what we call the derivative of f in the point x sub 0. Let's see an example. What happens if the function is a constant function? In other words, I do not care about the value of the x, the function is always c. Graphically, they are horizontal lines parallel to the x-axis. In this case, c is a real value and f of x is always equal to c. Let's prove that the function is derivable at any point on the line, no matter if you put x sub 0 here or any other value. Now we are going to calculate its derivative using this limit here. And that is very simple. To start, we rewrite the limit. The derivative in the point x sub 0 is equal to the limit when h tends to 0 of f of x sub 0 plus h minus f of x sub 0 divided by h. Exactly the same definition that is up here. What do we have to do? Notice what our function is. This function in 0 is worth c. In 1 it is worth c. This function in 2 is worth c. This function in x is worth c. This function in x sub 0 is worth c. And this function in x sub 0 plus h is also equal to c. To put it another way, this function is always equal to c. Therefore, how do we proceed to calculate the limit? F of x sub 0 plus h will be c, and f of x sub 0 is also equal to c. And this limit seems quite simple. It is the limit when h tends to 0 of c minus c over h. If I simplify a little more, it is 0 over h, but 0 over something is 0. Therefore, the limit when h tends to 0 of 0 is equal to 0. It is very easy in this case to calculate this derivative. So what do we have? The derivative of a constant function, no matter what the value that c has, is always equal to 0. Remember it, as it is a very important rule. Let's see another example. Now we also take a function that is very simple, which is the function f of x is equal to x. If the x is worth 1, the function is worth 1. If the x is worth 2, the function is worth 2. If the x is worth x sub 0, the solution is x sub 0. So let's try and prove if this function is derivable at any point x sub 0, and we will calculate its derivative. First step, exactly the same as always. I take the definition of the derivative and put it here. The only thing we have to do is to replace what is worth f of x sub 0 plus h with the value of the function and f of x sub 0 with the value of the function. This is very simple. The function is f of x equal to x. That is, what you put between parentheses is what comes out. That is to say, f of x sub 0 plus h is x sub 0 plus h, and f of x sub 0 is x sub 0. But now look at this quotient that has been obtained. The h was the denominator that there was. X sub 0 minus x sub 0 actually cancel out, and I am left with the limit when h tends to 0 of h over h. Now you have to be careful because you could say that this is 0 over 0, hence it is an indeterminate form. Yes, but before calculating the limit, we have to simplify. How much is h over h no matter the value of h? H over h is always 1, therefore the limit is 1. Obviously, what is the limit when h tends to 0 of 1? 1 is constant, therefore it is simply 1. The next important rule is that if we consider the function f of x equal to x, we find that it is always differentiable at any point on the line, and its derivative is 1. Here, notice that I do not put x sub 0, I put the function f of x equal to x, and at any point it is an x, then f prime of x is equal to 1. Perfect. Let's see another case. What happens when I consider the function f of x equal to x squared? Is this function derivable at any point, and what is its derivative? Let's have a look at it. We take again exactly the same definition that we have chosen at the beginning. Let's see. I am asked for x sub 0. Here I have f of x sub 0 plus h minus f of x sub 0. Actually, we have to determine what the function is in this case. The function is x squared. What does that mean? I don't care about the value you put in the parentheses. The function will take all of that and square it. That is to say, I have the following. F of x sub 0 plus h will be x sub 0 plus h squared, and f of x sub 0 will be x sub 0 squared. Let's see what we can do here. All I've done here is expand the square. X sub 0 plus h squared is, as you all remember, x sub 0 squared, the first squared plus 2 times the first times the second one. As you can see here, twice h by x sub 0 plus the second squared, h squared, minus, here I have simply removed the parentheses in the second term, x sub 0 squared. But be careful with this. You have to remember that here I have an x sub 0 plus h squared. It is a sum squared, therefore you have to apply the corresponding rule. Can something be simplified in this fraction? I think so. I mark it here now. X sub 0 squared minus x sub 0 squared, they cancel out. That is the initial point in which I am calculating whether the function is differentiable or not. Here we can see that it cancels out. So, what do I have then? 2h by x sub 0 plus h squared, divided by h, removing this and this for what is left. What can I do now? If you try to calculate the limit in a direct way, you replace the h with 0, I would be left with 0 plus 0, which is 0 divided by 0. It's an indeterminate form of 0 divided by 0. Can we do something? Yes, we can try to simplify. Perhaps you'll think about applying L'Hopital's rule. No, let's just try to simplify now to see what can be deduced. The first thing that comes to mind is that there are two h up here, and here actually there are two h multiplying. But I only want one of the ones I have here. I'm going to factor out the common factor of h, and what I am left with is the limit when h tends to 0 of h by 2x sub 0 plus h. But look, I have h up and h down. It's multiplying up here. Can I simplify? The answer at this moment is yes. And therefore, what I have left is the limit when h tends to 0 of 2x sub 0 plus h. What is the value of this limit? Change the h by 0, and I am left with 2x sub 0. That is to say, this limit exists. The function is differentiable at any point x sub 0, and its derivative is 2x sub 0. In general, we won't talk about x sub 0, but about an arbitrary point x. We have that the function f of x equal to x squared is differentiable at any point. This limit exists. I don't care about the value of x sub 0 you put, and its derivative is 2x. That is, f prime is equal to 2x. We already know the derivative of several functions. The constant is 0, the derivative of x is 1, the derivative of x squared is 2x. Perfect. Can this result be improved? Yes, in general, if we obtain the function f equals x raised to the power of n, not x squared, but x cubed, x to the fourth, x to the fifth, then we also have that it is differentiable at any point. For n positive, greater than or equal to 0, its derivative is simply x raised to the power of n minus 1. Notice what is happening. N decreases, and we subtract 1 from the exponent we had before. If n is negative, we need to be careful. The function is differentiable at every point except for x equals 0, as it is undefined at that point. If n is negative, we are referring to x raised to the power of minus 1, or x raised to the power of minus 2. In such cases, it is equivalent to 1 over x or 1 over x squared, respectively. In essence, it's undefined at 0. Nevertheless, the derivative remains quite similar. The rule is nearly the same, with a need for caution when n is negative. We've covered some key derivatives, including the constant function f of x equal to x, x squared, and an important one, x raised to the power of n, with its derivative being n times x raised to the power of n minus 1. I've covered these topics, and I hope they have been helpful for you. Keep in mind that you'll encounter these derivatives frequently. Thank you very much for your attention.